Today's video is brought to you by Lego Mummy and either my 3-year-old or 5-year-old's drawing. So from 5.1, we stated, and actually we used it, maybe it wasn't 5.1, I think it was 5.4 or 5.3, we stated this relationship. If b to the k equals a, or b to the k equals a, if and only if log base b of a equals k. That was essentially how we defined logarithms. And in both of these cases, b could not equal 1, and b had to be greater than 0. So what we're going to do in 5.5 is we're going to look at how do we solve equations in either of these forms. So recall that this form here is exponential, and this form here is logarithmic. So we'll start with solving the exponential equations. So there's two different properties we can use, and I believe MyMathLab uses, in their question helps, they use a kind of a variation on this. Now notice here in the notes, we're using a as our base for an exponential thing, so that this a is the same thing as this b. And this is saying if we have two bases that are the same, provided these properties are true, then their exponents must be the same. So for example, if I know that 2 to the x equals 2 to the 3x plus 1, then the solution to this is just solving x equals 3x plus 1, and I'm not even going to bother with that. You all know that. That property is also true if we work with two logarithms that have the same base. So if we have log base a of, say, 3x minus 1 equals log base a of, let's just make it x, kind of like before, then because these logarithms are the same base, then we would solve this. And we have to be careful because this might introduce extraneous solutions based on is our x value actually an allowed value within the logarithm. Okay, so here are a couple examples of solving exponential equations. Now, the problem with this one is it's going to be impossible to rewrite the left side so that it has the same base as the right side. So what we do is we use the logarithmic equality right here coupled with properties of logarithms to solve this. So I pick a logarithm of any base I want and I take that log of both sides. I'm going to pick a base of log of 2. So I'm going to take log base 2 of 3 squared, and that's going to equal log base 2 of 2 to the x plus 6. Now, here's why I chose log base 2. Recall that when you have an exponent, we can multiply by that exponent. I'm not really going to bother over here. I'm just really going to leave this as a log base 9. So this is the exponent. I'm going to pop that out of the logarithm and multiply by it using that property of logarithms. And then I'm going to note that I have log base 2 of 2. Well, recall that if the bases match what you're evaluating log of, then this thing equals 1. So this right side just becomes x plus 6, and the left side is log base 2 of 9. Now, log base 2 of 9 is just a number. We could use our calculator to evaluate it. It's irrational. It's not nice, neat, and clean. So I'm happy with this as my final answer. X equals, subtract 6 from both sides, log base 2 of 9 minus 6. That's a perfectly good answer. Unfortunately, MyStatLab will probably require you to enter this as a decimal. So let's check that out. I would type this in my calculator or in Desmos by going to my functions. Under miscellaneous, you'll see the log a thing. So I'll do log 2 of 9 minus 6, and there is an approximation of what our x should be, negative 2.83. I also want to demonstrate the graphical solution method here. The graphical solution method will get us this approximation. So here I'm going to graph y equals 9, and I'm going to graph y equals 2 to the, notice I'm putting parentheses, whoops, I didn't hit 2, 2 to the parentheses x plus 6. So this is the intersection method, and I see that I get my value of 2.83. Same value we got with our approximation. Okay, next example. This problem is exactly the same as this problem. The one difference is we do not have a base equal to a base. We have 5 times a base plus a number equals a base. So let's subtract the 8 divided by 5. We'll get 5e to the 6x plus 2 equals 12. Divide both sides by 5. We get e to the 6x plus 2 equals 12/5. Gross, but whatever. Now I'm going to do the same thing I did over here. I'm going to pick a logarithm of any base I choose. I'm going to choose log base e, which is represented by ln, at least in America. So I'll take that natural log of both sides, and I'm going to apply this property where this exponent here becomes what we multiply by. And then I would note that we'd end up with the same situation over here, log base 2 of 2. Here we'd get natural log of e, so all that's equal to 1. So we'd have 6x plus 2 times 1 equals natural log of 12/5. From here, this is just a number. Think of it like 2 and subtract 2 and divide by 6 and you're done. So x equals natural log of 12/5 minus 2 divided by 6. Well, of course, we got to follow MyStatLab's rules of round to however many decimals that we want. And so I'll type in my analytical solution method, analytical algebraic. It was this, minus 2. Note I'm going to do parentheses around all that and divide by 6. And I get approximately negative 0.187. Let's do a graphical method again. So I'll type in the left side, e raised to the 6x, plus 2, and that is equal to, I don't want to do that. Sorry, it was supposed to be plus 8, and then that's equal to y equals 20. I should have put a y equals over here just in case. All right, I'm going to hide all this other stuff that we got going on in here. And we need to find this intersection point. There it is. Y equals negative, or x equals negative 0.187. All right, so these last two examples are a very special example where we have to do some tricky algebra that you might not have thought of until you see it, and then now on forever you will think of it. So first off, note there are 3 unique bases that we're not going to be able to combine. So we're not going to be able to do what we did up here where we have some base equals some other base with various exponents and used our logarithms to eliminate the exponents. So first what we'll do is we'll get this thing equal to 0, and I want you to note something. So I'm subtracting 6e to the x and 16, it equals 0. Doesn't this look suspiciously similar to ax squared plus bx plus c, meaning the quadratic form? So I'm going to do a substitution. I'm going to say, let's let w equal e to the x and ask myself, what's w squared? Well, that's equal to e to the x squared, and if you remember your properties of exponents, you multiply these exponents, so we get e to the 2x. That means I can rewrite this equation by substituting in these letters for e to the 2x and e to the x, and I would get w squared minus 6w minus 16 equals 0, and here we are, a nice, neat quadratic. You can solve however you wish. Complete the square, quadratic formula, factoring if you can, graph it, whatever you want. I'm going to go ahead and factor this because it is factorable, and that's the fastest way. So that's w minus 8 and w plus 2 equals 0. So I get 2 solutions to this quadratic. W equals positive 8 and negative 2. Now remember, w is a placeholder for e to the x, which is the actual values we want. So we have then 2 equations to solve. E to the x equals 8, and e to the x equals negative 2. Now notice we have now created a base equals a base, and we can just use logarithms of both sides, and we'll have it solved. So pick any logarithm you want. Remember last time we had e as our base, I chose natural log because that eliminated that piece and left us with just an exponent. So I'm going to do the same thing here. Natural log of both sides. Note this just becomes x on this left side, and we get natural log of 8 on the right side. Bam, we're done. That's it. That's just some sort of number. So we'll do the same thing here. Natural log of both sides. And again, x equals natural log of -2. Bam, we're done there as well. But be careful. We cannot take a logarithm of a negative number. So this is, there's no solutions to this one. Maybe we should say no real solutions. So that's not a solution. Our only solution to this equation is natural log of 8. Now, of course, my stat lab is going to want you to show what that approximation is. So let's take natural log of 8 and see what that's about equal to. That's approximately 2.079. All right, let's do a graphical method. So in this case, I'm going to do y equals e to the 2x. That was the left side. I'm doing the intersect function. And then the right side was y equals 6 e to the x plus 16. Well, I switched the order, but whatever. So I got to hide these other two things. And it occurs to me that this is, maybe we wanted to do the intersect or x-intercept feature because that might have been easier to find, but that wasn't too bad, right? There it is, 2.079. This last problem is the same problem, except we have to deal with this negative exponent. So I think the first thing I'm going to do is get everything on the left side like I did over here. So subtract that 4e to the negative x, subtract that 1, we get 0. I'm then going to remind you of that special property of when you raise something to a -1, that's really division by it. So this is really e to the x minus 4 divided by e to the x minus 1 equals 0. Well, that means we have to be careful. We cannot let this happen, right? If that happens, then we get in those solutions we have to exclude from our solution set. Well, if I solve this, I'll take natural log of both sides, I'll get natural log of 0. Hey, there's no solutions to this. So we don't have to worry about this being division. All right. Now, if you recall back from our rational functions, to eliminate division, we would multiply by the denominator. That's e to the x. So I'm going to multiply all of this by e to the x. Technically, I'm multiplying this side by e to the x, but 0 times anything is 0, so who cares? So e to the x times e to the x, we're going to add those x's together. They'll end up 2 of them. And then minus 4 times e to the x divided by e to the x is just minus 4. And then -1 times e to the x is negative e to the x. Well, look at this. This is the exact same problem we did back here. It just took us a little bit of work to rearrange the equation so that we could see it was the same problem. Now, you might need to note that it would be e to the 2x minus e to the x minus 4 equals 0. And then we'll do our same substitution we did over here. W equals e to the x. W squared equals e to the 2x. So I'm going to replace this with w squared. I'm going to replace this with w. And away we go. This is nice and factorable. Or is it? Oh, it is not factorable. So let's quadratic formula it. So w is going to equal negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. All right, what does this simplify to? Let's see, 1 plus or minus. So this is positive 16. This is 1, so it's going to be the square root of 17 over 2. Well, remember that what we're solving for is x, not w. So we have two solutions here. E to the x equals 1 plus square root of 17 over 2, and e to the x equals 1 minus the square root of 17 over 2. Well, at this point, this is just a number. Nasty, agreed, but just a number. Notice that this number Because the square root of 17 is greater than 1, when I subtract that from 1, this is all less than 0. So there's no solutions to this one. But this one, when we take natural log of both sides, it's whatever this gross terrible number is. Well, that's why we have technology, right? Let's just smash this in Desmos and see what pops out. So natural log of 1 plus the square root of 17, and then all of that, come on now, there we go, all of that divided by 2. So our number is approximately 0.817. I will let you try the graphical method on this one.